Hi, it's Romeo Bruni and welcome back to the Astronomy channel. Today I'm talking about a very exciting topic, a relatively new one in astronomy, and that's fast radio bursts. Before we get too far, I'd like you to please subscribe to my channel so that I can reach out to further people. Fast radio bursts, what the heck are they? Well, it's a very new phenomena in astronomy, only in the last 20 years or so. And what they are very brief, lasting milliseconds. The longest ever was 3 seconds. Many are 1-2 millisecond. That's a blink of an eye is 200 milliseconds, which is a fifth of a second. So this is 1/200th the blink of an eye. And it's a very fast, transient, meaning it comes once and usually doesn't come back. Extremely bright burst of radio waves that are coming from extragalactic sources. And how we know that is very important. The very first one ever discovered was by an astronomer by the name of Duncan Lorimer. And Duncan Lorimer in 2007, while searching for pulsars in our galaxy, discovered this. And this has been termed now the Lorimer burst. If we look at this Lorimer burst, we're plotting frequency of the light arriving on the y-axis versus the time it takes to arrive. So it goes down like this. What this means is that even though at the time, whatever's releasing these extremely powerful bursts of energy, whatever is releasing them, at the time it's released, it's all released at the same time, and it would look like this. But by the time we receive it, it's shaped more like this, meaning that the lower frequencies are coming in later than the higher frequencies. But what's with that? If you say that the speed of light is the same for all objects, how come we're getting that kind of distribution? Well, the fact remains, and it's a very important one, that the speed of light is the speed of light in a vacuum. But if light is not going through a vacuum, and let's be honest, there's no vacuums in the universe. It's never really in a true vacuum, so it's always going through a medium. And the speed of light in a medium is not constant. Light slows down in any medium. And the speed to which it slows down is proportional to its wavelength. The longer the wavelength, the lower the frequency, the lower energy, i.e. red light over blue light, for example. The higher the wavelength, the more it's slowed down. So light, even though when it's first emitted from a fast radio burst, is all the light is emitted, all the frequencies are emitted at the same time. When you plot frequency versus time of arrival, by the time it actually gets to us, because it's transversed through the universe, the lower frequency light is going to be slowed down more than the high frequency light. And the amount of slowing down is directly proportional to the amount of universe that it's gone through, because it's related to the integral of the electron density, the free plasma density, amount of universe it's gone through. And this very important principle of light slowing down based on frequency is called dispersion. And the dispersion measure, dm, is actually a direct proxy for distance in the universe. dm, of course, in this case is dispersion measure, not dark matter. So Lorimer discovered this first fast radio burst in 2007, and they weren't sure what was going on with it. They did realize something very important with it, and that was that the dispersion measure of it was extremely high. Now, thanks to pulsars, they had sorted out dispersion in the Milky Way very cleanly. And if you remember what pulsars are spinning spinning neutron stars that emit a radial pulse at a very regular rate. So if you remember neutron stars, when stars die, if they're very low mass, under 2-3 solar masses, when they die, they become a white dwarf. For stars of a much higher mass, when they die, if they're very high, they become a black hole. If they're sort of more intermediate, they become a neutron star. And a neutron star is an extremely dense star that's approximately the size of Manhattan. They're about 10 kilometers across. They weigh 2 to 3 solar masses. You remember white dwarfs cannot weigh more than 1.44 solar masses. Neutron stars weigh approximately 2 to 3 solar masses. They can't weigh more than that. So they're very regimented size. And neutron stars, when they're young, they can be called a pulsar because they're very young and they have a lot of spin energy. They're spinning very rapidly and they have huge magnetic fields. And the combination of the spin and the magnetic fields emit a very regular pulse that's whipping around, and every neutron star has its own very specific pulse. And it's whipping around, and we are in the line of that beam, and so we'll see a beam every 60 seconds or a beam every 100 seconds, depending on the particular pulsar. So it's by measuring pulsars in our galaxy that we were able to sort out this idea of dispersion. Now, in our galaxy, of course, the pulsars are all going to be distributed in the galactic plane because pulsars are nearby neutron stars that we see, and they have to be in our galaxy because they're relatively low energy. But because they are in our galaxy, once we identify a pulsar, we can use parallax and other methods to exactly determine the distance to the pulsars in our galaxy, and then compare that with the dispersion measure that we get from the pulsars in our galaxy. And that enables us to map out exactly in the Milky Way. We can map out the electron or free plasma concentrations in the Milky Way using radial pulsars. So we know exactly where the electrons, the free electrons, are in the Milky Way. So we can use that information to then start to decipher what's going on from these pulsars. So Duncan Lorimer found the first one in 2007. It wasn't until many, many years later that they found any more. And at first they thought, well, what's going on? Why aren't we finding more? And the reason we're not finding more, or weren't finding more, is that radio telescopes have a very tiny field of view. So they're only looking at a very small patch of the sky. Where Duncan Lorimer first discovered his fast radio burst, it was the Parkes telescope in New South Wales, Australia. And the field of view was about the size of a full moon. So it's a very tiny field of view. Of course, he was looking for radio pulsars, and finding this fast radio burst was a serendipitous discovery. He wasn't looking for them. He was looking for pulsars in our galaxy, actually pulsars in the Magellanic Clouds, which are neighboring galaxies to ours, which are very close. And he found this. It wasn't until many years later that, using Parkes again, they found other fast radio bursts, and then determined that, oh, this is a common phenomena. And they started to sort out and started to dig into A, where are they coming from, and B, what the heck are they? Now, where they're coming from, as I pointed out, that when we measure these fast radio bursts, when you take the DM, the dispersion measure, the levels are very high, and max in our Milky Way using our archaic units are 35. And these fast radio bursts that are extragalactic have dispersion measures of 350, which means they're coming from very far away. we'll get into what they are shortly. But let's look at what they look like. Now, a fast radio burst is coming from far away. Let's say there's a galaxy far, far away, and it emits a fast radio burst that eventually reaches the Earth. So when we're trying to sort out the dispersion measure for that fast radio burst, the things you need to consider is the dispersion that happens when it goes through from the host galaxy. And then host galaxies have a halo, and it'll go through that halo, which will also disperse. And then it goes through the intergalactic medium before it reaches the Earth, which is in the Milky Way. And so it has to go through the halo and the Milky Way. Luckily, we know exactly the amount of dispersion that we're going to get from the halo, from the Milky Way, not the halo quite yet. So we can subtract that. We can sort of approximate what's going on from here. So it gives us a kind of an idea of what's happening in the intergalactic media. That's the most important aspect that you can take from this talk, that even though at this point we may not know exactly what's causing them, the fact that light, as it's after it's emitted, by the time it reaches us here on the Earth, can be affected by the media that it's passing through, is a very important phenomenon in astronomy. And that phenomena is called propagation effects. Propagation effects. The most important propagation effect, of course, we've discussed already, is the DM, the dispersion measure. The DM is basically a proxy for distance. It's a proxy for redshift. It's a proxy for Z, which is a summarization of the redshift, which is how far things are away. There's other propagation effects that are very important that can affect the light. There's propagation effect called scintillation, which is the reason that stars twinkle, because of scattering of light by particles while it's traversing the universe. You get scintillation. A slightly different phenomena is called scattering, and that's also a propagation effect. The scintillation and scattering are reflections of the clumpiness of the intervening matter. Remember, the DM is a proxy for the total amount of material that's there, which is a proxy then for distance. Scintillation and scattering, which they can analyze from the actual propagation wave, gives them an idea of the clumpiness of the material between where light was emitted and the time it gets to us. And there's a fourth important phenomena, and that's something called Faraday polarization. Now, light is polarized when it's all coming in at the same polarization frequency. Most times light is not polarized, but sometimes light in certain situations, especially when emitted by in high magnetic fields, all have the same polarity. And just like the other propagations of effects, the dispersion measure, scintillation, and scattering, the Faraday polarization, that's the angle that the light is polarized at, varies with the frequency. So that too is going to depend on the frequency of light. And that's in the Faraday polarization is important because that gives us information with regards to the total magnetic field that the light has passed through during its travel to the Earth. So even though we may not even know what's generating an actual fast radio burst, the propagation effects, or how that light is affected as it's left its emitting source, and by the time it reaches us, the propagation effects gives us a wealth of information with regards to the media, the intergalactic media that it's passed through, how much there is of it, the total magnetic field, the clumpiness of it, i.e. with the scattering and scintillation. So fast radio bursts are a wealth of information. What do they seem to look like? Well, most importantly, fast radio bursts are not a standard candle. Whatever seems to be emitting them, the energy level is extremely variable. It can be sort of similar to pulsars in our local galaxy, very low energy, or they can be extremely high energy. In fact, the furthest fast radio burst ever detected was like 3 billion light years away. And it was determined that the energy involved in that was like 1 trillion times what we get from a radio pulsar. It's the amount of energy the sun emits in 3 years is emitted in like milliseconds. So the amount of energy emitted can really vary, which of course determines through sensitivity how far away they are. Obviously, the furthest ones away are going to be the very brightest ones, because by the time they reach us, they're low energy, but they started off so high that we're seeing them at extremely great distances. So that's very important. In fact, the relationship, interestingly, between the dispersion measure and distance was analyzed by a professor, a very great gentleman, J.P. Macquart, who unfortunately passed away the year he discovered this relationship, which astronomers now refer to as the Macquart relationship, which is a measure of dispersion versus Z. And Z is a proxy, of course, for distance. So the higher the dispersion, the further away something is. So it's the Macquart relationship is the actual physical relationship between the dispersion measure and the distance. Here's another little graphic showing you the Macquart relationship and what's happening. Light leaves the emitting source. It has to go through the halo and the galaxy itself, through the intergalactic media, then has to go through our Milky Way. We map these things, and that gives us a lot of information then on the path that it's followed through. There's a picture of J.P. Macquart himself. So here's a little thing of describing fast radio bursts. Of course, with these things I'm holding up, you can always just stop the video and take a close look at the information being illustrated there. Okay, so going back to fast radio bursts. Their luminosity, which is the strength of the initial emission, is extremely variable. They can be light fast radio bursts, not too bright fast radio bursts. There can be extremely bright fast radio bursts. So the energy emitted every time one goes off can be extremely variable. So that's the luminosity variable. Now the other things that are variable are the band that you see. And if you remember your old radio band, my old favorite channel was a CFRB 1010. That came in at a very specific band. And that's why you could turn your radio to that band and you only get that. But when fast radio bursts go out, they are broadband, which means that it's not at a specific frequency. It comes in at a wide range of frequencies every burst. If we were to measure the band versus the actual FRB, some are coming in a band from this gigahertz to this gigahertz. Some are longer from this gigahertz. Some are down here. In other words, just like the luminosity is random, if you will, and can really vary a lot, the band that it comes across to you is also varying a lot. Also, what will vary a lot is the duration of the fast radio burst. even though most are measured in milliseconds. Some are measured in microseconds, which is like a millionth of a second. And the longest fast radio burst ever discovered was 3 seconds. So the luminosity can vary incredibly. It can have different broadband, come in at different frequencies. The duration can vary. So none of those things are standard candles, if you will. So none of those things particularly give you much information. But once it's actually emitted, as it goes through, the propagation effects that we described earlier will give you a ton of information about the intermediate material, even though you may not know exactly where the fast radio burst initially caused it. Okay, so now interestingly, so when they first found the first fast radio bursts, because radio telescopes have a very poor angular resolution, for example, the Parkes telescope has an angular resolution about the size of the full moon. So if there's a fast radio burst, it'd say, oh, it happened from this spot in the universe, somewhere within this full moon size. The problem with that is with deep field viewing of, for example, a full moon size, for example, with the James Webb telescopes, there will be 1,000 galaxies in there. And you need to pin it down more exactly than that to find out, to try to get information, well, what's causing these? So that's why, first of all, it took so long to find a second one, because you're only looking at a tiny, tiny patch of the sky. But eventually they found some that, and we're going to get into this, that were repeating. And once they start to repeat, then you can train all your other telescopes and all the different multi-messengers. You can use all the different light frequencies to train your telescope, or you can use cosmic rays or gravity waves or neutrinos. You train all your telescopes to that spot in the sky that's repeating. And radio telescopes that use interferometers are basically a bunch of radio telescopes that are interconnected, and then they use extremely powerful computing, and they basically can do a triangulation of the messages coming into us, just like they can pinpoint where you are on the Earth by triangulating your distance to various satellites in the sky, by measuring the slight difference in timing of things coming into different radio telescopes using interferometer. They can pinpoint very exactly in the sky where these fast radio bursts were coming from. And they've been able, by doing that, to identify the galaxies, the very important galaxies, that here's an indication of the poor angular resolution that you get and how you need to pin it down. So then using, for example, very sophisticated interferometers, and using this technique, they were able to pinpoint, and this is the first time they didn't use the Parkes telescope. They used the Arecibo radio telescope in Puerto Rico, which unfortunately now is decommissioned. They had a mechanical issues and it's no longer functioning, but it was the Arecibo telescope that found the first repeater, and that's been labeled R1. Now, the duration of this repeater being in milliseconds, right, gives you a limitation on how big the object is. If its signal is being transmitted and it only takes like a millisecond for it to come, the light transit time in 1 millisecond is only a certain number of kilometers, a few hundred kilometers, whatever. And so it tells you that the emitting object or emitting thing can only be that big. If it was bigger, it could not emit such a short period of time. The other thing, this very famous R1 that the Arecibo telescope found, was that it was the first repeater, which means that if something is repeating in the sky, it cannot be, the cause of it cannot be a cataclysmic event. For example, if a black hole or two neutron stars or a neutron star, a black hole, whatever combination of things is merging, obviously when it merges, you're going to get a one-time event, a cataclysmic event, and you're never going to get information from that again. Similarly, type 1a supernovas, which are when white dwarfs accumulate material, get over the Chandrasekhar limit, and explode, totally annihilating everything. That's the most important standard candle in astronomy, because it's a total annihilation, meaning that exactly 1.44 masses, solar masses of energy are released every time. That's a perfect standard candle because it's the same amount of energy released. They, of course, never leave a neutron star because there's total annihilation, but core collapse supernovas will leave a neutron star. But of course, they are also a one-time event. You're only going to get one core collapse. So when we started finding repeaters, then we realized that cataclysmic events are impossible. The duration of the event is so small, we knew it was coming from a very small object. Now, as a Canadian, I'm very proud to say that the most important, by far, radio telescope in the world is in Penticton, British Columbia, and it's called the CHIME. The CHIME, and CHIME is for Canadian Hydrogen Intensity Mapping Experiment. Now, CHIME was originally built as a cosmology experiment. It was initially built to detect 21 centimeter hydrogen. Now, what happens is when an electron in hydrogen, cold hydrogen, jumps from its second level to its first level, it emits a photon of light that's going to be very specific, of course, another kind of standard candle. It's going to emit a light at 21 centimeters or wavelength. Now, that light, once it's emitted, it's always going to be emitted at exactly that energy level. But by the time it reaches us on Earth, because of the universe's expansion, that light is going to be redshifted, which means the frequency that we detect this 21 centimeter is not going to be 21 centimeters. It's going to be stretched out. And the amount of stretching is proportional to the universal expansion. So CHIME was originally designed to detect that, but then that's kind of serendipitously, it started to discover all these fast radio bursts. So it was designed to discover, to look at hydrogen, and also they knew it was going to help us with radio pulsars, because obviously it's going to detect the radio waves of those pulsars coming in. But it was very nice when suddenly it started to detect all these others, fast radio bursts. So there's a picture of CHIME in Penticton. This length here is like 100 meters, and each one of these are like 20 meters. So this is a huge apparatus. And it's not one radio telescope, but a thousand, maybe 1,000 and something radio telescopes, each hanging from one of these things. And then it uses intensive computing to use a little bit of interferometer between them to try to localize where the fast radio burst is coming from. Now, it unfortunately, like Parkes, is, even though despite this attempt to localize, can only localize to the size of, again, a full moon, which isn't enough localization to say it's exactly that galaxy. So they need other radio telescopes down the road to keep looking in that site, hope to find a repeater, and then if it's repeating, they can use other methods to figure out, if it's repeating, they can then pinpoint the exact galaxy that it's coming from. Now, what makes CHIME so effective is not so much because it's decreased the angular resolution to pinpoint where the galaxy is coming from. It's because its technique has increased the field of view so dramatically that it spans basically the whole northern hemisphere simultaneously. It's a transit telescope, meaning it's not moving, and as the Earth rotates, it's oriented north-south. So this is like north-south is like this, and as the Earth rotates under it or over it, however you want to look at it, the sky is moving across it, so it's seeing every day the whole northern hemisphere. So if something is repeating, then it's going to see it. Now, this concept of repeating is very important because it gives us hints as to what's going on. And luckily, they found finally a fast radio burst that came from our galaxy. And when they went to that spot in the galaxy, they found one star that was there. And this star that was there, it was called a magnetron. And a magnetron is essentially a neutron star that is particularly young and particularly energetic in terms of a magnetic field. So they are very young, powerful neutron stars, pulsars, if you will, but very powerful with powerful magnetic fields. And what happens is that either there's some kind of star quake that happens with this magnetron, and it emits a burst of radio waves, or some kind of material comes near it and material funnels into it, and so it releases a fast radio burst. So magnetrons are considered by far the most probable cause of fast radio bursts. In fact, they've been more or less confirmed to cause a good majority of fast radio bursts, if not all, because you can map the repeaters versus the non-repeaters. Now, CHIME has become so awesome that it's detecting maybe 10 fast radio bursts a day. And it approximates that if it was able to see the whole sky all day, all time, we would be seeing maybe 1,000 a day. Now, of the maybe, let's say, 1,000 fast radio bursts they've now found, less than 10%, or approximately 80 or so, are repeaters. But the repeaters are very important because we can look at that spot in the sky and follow it over time and watch. And what happens is when we start to compare the repeaters versus the non-repeaters, there are differences between them. The repeaters tend to be, as we see here, broader bandwidth, and the duration is longer, versus the non-repeaters. They tend to be a narrower broad length and short duration. So there kind of seems to be a difference between repeaters and non-repeaters, which tells us that in the end, there may be two different types of things that are causing fast radio bursts. If you remember what releases fast radio bursts and what releases polarized light, there's a phenomenon called synchrotron radiation. And synchrotron radiation is when electrons are traveling at relativistic speeds, that means they're traveling super high speeds, near the speed of light. When electrons traveling at relativistic speeds are accelerated perpendicular to their velocity, they release synchrotron emission. Naively, I thought for a long time that photons were only emitted when an electron jumped from a higher orbit to a lower orbit, and then it would emit a very specific frequency of light at that point. But no, light is emitted by various other sources in the universe, an important one being synchrotron radiation, which is just electrons being accelerated without jumping from one level to another, will release radiation. Of course, to accelerate relativistic electrons, you can only, perpendicular to their motion, you can only do that when you have extremely powerful magnetic fields. It's magnetic fields that do that, and that's why magnetrons are a natural cause for this. The other thing that happens is when, let's say you have a source and it's emitting electrons in that direction, the synchrotron radiation is emitted perpendicular to the line of light, and that perpendicular light is also highly polarized. So synchrotron radiation is highly polarized, and the majority of fast radio bursts that we see are highly polarized. So magnetrons are definitely at the highest potential to be the cause. So those are magnetars, fast radio burst repeaters. Very interesting that a very important fast radio burst, and it's the only one they found like this. And that's fast radio burst 1809-16. Well, let's just take a quick peek at 1809-16. What does that mean, 1809-16? 1809-16, the first two numbers refer to the year. So if it was, basically it's the date that it was found. So 1809-16 means this was discovered in 2018, September 16th. So on September 16th, 2018, this FRB was first discovered. If you find something, an FRB, more than one FRB on that day, the first one is going to be 1809-16A. The next one, etc., is going to be B, and so on. So, and this one, the important thing about this one is I'd like to call it the old faithful of fast radio bursts, because of all the fast radio bursts found, yes, maybe 100 or so are repeaters, but of those repeaters, they're very erratic and random when they repeat. We can't predict. It can be in 2 days, or you look and it's not another one for 2 years, or whatever. We have no idea. But this one FRB 1809-16, repeats exactly every 16.4 days. Now, what really happens is that you have 12 days where you have nothing, and then you have 4 days over which you start to get your bursts, your fast radio bursts. And then it goes quiescent again for 12 days, and then over another 4 days you start to get the bursts. Inside that 4-day span, it's very unpredictable when the bursts will come. It's irregular. The power of the bursts will vary. So a lot of things vary, but they do come very periodically. So this particular fast radio burst almost for sure has something to do with that magnetron being a magnetar, I might have said this wrong earlier. Magnetar is the name, magnetar. This particular magnetar must be in a binary orbit with another object. So when two objects are rotating, about half the stars in the universe are in binary orbits. They're in orbit with another star. Periodically, it goes through a zone which causes eruption. So this magnetar is probably in a binary object. If we map one last little graphic I'm going to show you, showing our radio telescopes in the transient phase. When you measure luminosity versus duration, we have fast radio bursts, and then a very low energy, of course. We have our pulsars, we have from the Crab Nebula. The Crab Nebula is probably the most famous pulsar, because the Crab Nebula, when they discovered it, there are ways that you can work backwards and determine how old neutron stars are. And they're very young neutron stars, and they worked backwards and found that the a neutron star at the center of the Crab Nebula was about 1,000 years old. They worked backwards, and they figured, oh, there must have been something in the sky happening around 1000 AD. And then they checked all the historical records around the Earth, and at all different parts of the Earth, they found different cultures recording a supernova in 1054, i.e. a new star in the sky. And this new star in the sky over 2 or 3 weeks was visible during the day. So not only was it a new star, but it was an incredibly powerful new star. And it turns out that that supernova, of course it was a type of core collapse supernova, happened in 1054. And the pulsar that remains at the center of this Crab Nebula, of course, when it explodes, it sends out emitting shock wave of material, which is your nebula, and that's the Crab Nebula. So let's finish off here. Fast radio bursts are a new probe of the universe, a very important probe of the universe, for two very important reasons. A, the cause of them, whether they're magnetars, or something similar, is information about a new physical process or entity in the universe that we hadn't been aware of previously. So what is causing them? But more importantly than even what's causing them is the information that can be gleaned from the fast radio burst because of the propagation effects that affect light. And again, to summarize that, the speed of light in a vacuum is constant, but the speed of light in materials are not constant. And the speed of light in material is going to depend on frequency. That is exactly the same reason, for example, that you get a rainbow. Because if you shine white light through a prism, it slows down. And the amount of slowing down depends on its frequency. So red light slows down more than blue light. So it gets dispersed and you get a rainbow. So propagation effects are very important. The fact that light does not travel at the same speed in all media is very important. So fast radio bursts, I hope you enjoyed this talk. Don't forget to subscribe to me in my channel, and hopefully in the future I'll be coming back to you with another interesting astronomical topic. This is Romeo Bruni. Subscribe. Thank you very much.